Hello and welcome to my presentation. And thank you for the organizing committee for inviting me to give this presentation. I wish I could be present there in person and would also visit your lovely city of Baghdad. But unfortunately, due to the epidemic, travel is severely restricted nowadays. Maybe another time I'll have the opportunity to come and meet you in person. My name is Errol Güler. I'm currently an adjunct professor at George Mason University in the United States of America. And I worked many years as a professor at Boğaziçi University, and now I am emeritus there. My presentation will be on the subject of geotechnical design of complex buildings and infrastructures in Turkey and innovative solutions using geosynthetics. So I hope it fits your theme of geotechnical challenges of mega infrastructure projects, which is the theme of your conference. And I want to show you some examples with the aim to share with you what the lessons we learned were. The first project I want to mention is a deep excavation for a shopping mall construction. Here is the finished shopping mall, as you can see. It has a relatively low height because that is the restriction. It is located in a very popular area of Istanbul. And since the land is so expensive, the owners decided to put a big majority of the shopping mall and also the parking garages underground. And that's why they decided to have a 40-meter deep excavation. And interestingly enough, also the dimensions of these of the plan are about 40 meter by 40 meters. So at the end, when the excavation was completed, the space looked like a cube. And there were many buildings next to the excavation. On this side, they were at zero distance. Here, the buildings were also very close, and there were two narrow streets on each side, and across the streets, of course, there were also buildings installed. We used many instrumentation, including inclinometers, optical survey, extensometers, load cells, etc., throughout the construction period. Of course, limit equilibrium analysis were conducted, and I have chosen this cross-section to show some of the difficulties. This is the excavation, and this is the narrow street that I mentioned, and across the narrow street there is a building at one location that has several basements, and these are the anchors that are necessary to push this potential failure surface further back to provide enough factor of safety. So obviously you cannot put in this zone such long anchors. And so we had to choose at this location a combination of soil nails and pre-stressed anchors. Of course, in such a project, it is very valuable to have a finite element or finite difference analysis, which analyzes the stress strain behavior, because the deformation that this shoring makes is of uttermost importance, because it also determines how much differential settlement occurs under the buildings next to the excavation. And those of you who are familiar with finite element analysis know that the stability can be predicted quite successfully, but the prediction of deformations are extremely difficult. And in such a deep excavation, the rule of thumb is that the allowable deformation is limited with 0.2% of the height of the excavation, which corresponds to 8 centimeters. And we aimed in the design a deformation of the size half of it, namely only 0.1% of the height. And the measured maximum deformation was 5.5 centimeters. So considering the size of the project, it was a very successful prediction. And here you show the graph, how the deformation increased with time, which means with the advancement of the excavation until it finally reached 5.5. And as you can see, the deformation starts gradually, and as the excavation gets deeper and deeper, it picks up quite rapidly. Here is a picture from underneath the supported facings. You can see the traces of the pre-stressed anchors. Here is a neighboring building. This is a panel of which the purpose was that people wouldn't look into the excavation pit because they would be frightened. And from location to location, you see such funny struts. Their reason for being placed there was the project manager who said we should give the people who look into the excavation pit a little bit insurance that there is a support mechanism. So it's not actually doing anything there. It's just for psychological show. Here you see another picture with a few more struts. And you can see here this building and the one here along this side are literally at zero distance to the excavation. So this is the building wall and this is the facing of the shoring. And this is a picturesque photograph of the excavation with the correct sun direction. And this is the, again, final building in operation. What was the lesson learned from this project? It was only possible to predict the deformation precisely because of the vast experience of deep excavations in similar formations. These previous cases helped to calibrate the geotechnical parameters, especially the deformation parameters. You very well know that determining strength parameters from geotechnical soil investigation can be done quite successfully, but stress-strain behavior is very difficult to determine precisely from site investigation, and hence that is the reason why we have this difficulty in finite element analysis to predict the deformations correctly. So the conclusion is, instrumentation in excavations, regardless of depth, is crucial to calibrate the finite element input data for future projects. So you should not say, this is a small project, why do I need instrumentation? Well, if you instrument your excavation and calibrate your finite element models soil parameters, then this accumulates, and in a big project like this, you can successfully use this information. This is another project where several high-rise blocks of 26 floors residential buildings are constructed on a very deep alluvial deposit in Bursa. And as you can see from the SPT data, up to a depth of 25-30 meters, the average SPT number is 20, and they go as low as 10 and 15 at certain locations. So naturally, pile foundations have been used. Again, instrumentation is very useful, especially if you have to build a lot of piles for a lot of buildings in the same surrounding. Because the main difference between a pile load test and an instrumented pile load test is the following. When you conduct a pile load test, you can only determine whether the pile can carry this load successfully or not. But if you conduct an instrumented pile load test, that means you have measurement of vertical load at certain intervals of the pile, and typically what we do is we place these instruments at the locations where the soil stratification changes. You can determine how the stress is distributed. For example, if you have an external load of 450 tons, you can say this first section carries 100 tons, this another 100 tons, this another 100 tons, this another 100 tons, and then automatically the tip carries 50 tons. But this is valid only at the ultimate failure load. Under working stresses, for example, if you are loading the pile, let us say you apply a factor of safety of 3 to this load, the force actually dies out at a depth of maybe 7-8 meters. If you increase the load to a level where the factor of safety is 2, the stress dies out at maybe 12-13 meters. And the full capacity or the shaft resistance and tip resistance develop only if you apply the full load to the pile. And therefore, since you have all this data in hand, you can optimize your pile foundation. One way of improving the pile load tests even further is, instead of using an external pile load system, which necessitates huge reaction systems, especially for large size piles, you can use an Osterberg cell. And what the Osterberg cell does is it's actually nothing else but a jack which pushes the upper portion of the pile up and the lower portion of the pile down, and you build a shaft resistance in the upper portion directed downwards, and in the lower portion directed upward. And you can put this closer to the tip, so you can measure exactly what the tip resistance is, for example, if you are creating an end-bearing pile. So you really don't have to rely on the correlation between soil strength data and pile design parameters. Here you see the sister bars, which have strain gauges on them installed in the cage. And here you see layout of instrumentation with the cabling, etc. And as I shown before, you can see the stress distribution for every load step. So when you take the load here and here at a certain step, you exactly know how much of stress is being carried by this section of the pile. So you can play with the diameter, you can play with the length of the pile and create an optimum pile dimension. Same approach can be also used for lateral pile load tests. Again, when you conduct a lateral pile load test in an important project, you only can determine what is the ultimate capacity. But if you instrument your pile with strain gauges and with an inclinometer, then you can both measure the moments at these locations, and also with the help of the inclinometer, you determine the deformed shape. For example, if your aim is to provide a lateral restraint, this data shows this portion of the pile is completely useless. So you may build this pile portion or not, the deformation will not change because the lateral deformation ceases about at a depth of about 6 meters. So let us say with some safety you can make your piles 8 or 10 meters deep, but there is, for example, no need to make them 16 meters deep, and this brings an enormous saving. So what is the lesson learned? Pile load tests on instrumented piles do not only verify the design load, the data gathered can be used for optimizing the solution. Data gathered further can be accumulated in a database and can help improve the parameters prediction for future projects, like I have mentioned for the deep excavations as well. And the instrumentation of piles is extremely useful also for laterally loaded piles. Another deep excavation project in which I was involved was the Soho deep excavation design, which was conducted adjacent to a metro excavation. Here the depth was slightly less. It was only 23 meters for 7 basements. There were also adjacent buildings, similar to the first project I mentioned. But more importantly, there was an adjacent shaft and a pedestrian tunnel being constructed at the time. So the owner of the project, Soyak project, didn't want this shaft and tunnel to be completed to conduct his own excavation. So while the shaft was still with the temporary support and the tunnel was being constructed, the owner wanted also to complete the excavation and start the construction of the building. So it was a very complex project. Extensive instrumentation, of course, again was used, inclinometers, optical surveys, extensometers, load cells, strain gauges, etc. And compatible deformations and stresses with the design was analyzed. Here you see the excavation completed, and here you see the plan. This is the shaft, which is only 2.5 meters at 2.5 meters distance from our excavation, and had a diameter of 6 meters. And this is the pedestrian tunnel, which had a 7-meter diameter and was only 6 meters away from the excavation and at a depth of 20 meters. So it was passing almost towards the bottom of the excavation. And there is no way you can analyze such a condition with the traditional limit equilibrium or even two-dimensional finite element analysis. So what was done was a three-dimensional finite element analysis. As you can see here, this is the excavation shore, and these are the struts. And to model the shaft and the rock bolts, and this is the connection of the pedestrian tunnel to the shaft, and this is the pedestrian tunnel under construction. Similar problems exist where two-dimensional analysis is not enough to provide the solution. For example, in this project, the municipality wanted to construct a bridge crossing on pile foundations, but there was an existing metro tunnel line here. So the double tube existing metro tunnels were around a depth of 15 meters, and bridge foundation located here, right very close and to either side of the and in between the metro tunnel. And the effect of proposed piles on existing TBM tunnels needed to be known. This is of uttermost importance because if there is a slight deformation on the metro line, the metro operation may come to a halt, and this means millions and millions of loss and a very terrible service cut down for the customers. And from the excavation of the board pile phase to the concreting and then of the loads that will be transmitted to the piles by the superstructure has been modeled. Here you see various soil stratifications And here you see the stresses that were determined on the tunnel lining. And of course, these stresses were compared with the design, the original design of the TBM liner system. And it was shown that this additional stresses caused by the pipe foundations were within acceptable limits. Another interesting project where a three-dimensional behavior was necessary was again a deep excavation, this time adjacent to a highway tunnel and portal. Here you see the portal of the highway tunnel, and because of the topography, the portals are slightly asymmetric here. And this is the excavation for the construction. And as you can imagine, the tunnel has a protection zone, so they don't allow any part of the structure to intrude into that protection zone, even the anchors. And therefore, a very complex analysis and project has been developed for this 4 to 5 meter deep excavation here. And again, metro tunnels actually are a little bit more stable because they are circular in shape and approximately 7 meter in diameter, where highway tunnels have an opening of approximately 16 meters. So the stresses on the highway tunnels are much more critical. So the solution found was a two-stage excavation, and what that was the property boundary. So since land is so expensive, they wanted to use all the boundary. So what was designed was a shoring here, which was permanent, and then a temporary shoring, which was leaving a berm actually. And after part of the buildings were constructed, struts were extended to this upper portion, and this lower portion was excavated by again placing struts to the construction. So it is a very complex analysis. Again, if you don't know the soil properties extremely well, all the analysis that you do just will lead to excessive deformation, which you would not like. So as I mentioned in the first example, of course, the analysis method is very important. And again, this problem cannot be solved with a two-dimensional finite element analysis, but also without proper parameters, again, the analysis is not worth anything. Another very interesting and complex problem was the Maslak 1453 housing and commercial complex. Basically, this project was built around a hill. This is the hill, and it surrounds this complex, buildings complex surrounds this hill and has a surface area of 322,000 square meters. So this is not building area, it's the surface area on which this complex, these building complexes are constructed. The total construction area is 1,700,000 square meters. There are a total of 24 towers ranging in height between 51 and 21 floors, and parking garage for 11,000 vehicles, because there are also shopping malls, concert halls, theaters, movie theaters, etc. And a shopping street that extends throughout the whole complex, which was 1,453 meters long. Here is a model. This is the hill that I was mentioning, and these are the building complexes. So they look like they are individual buildings, but this is actually one whole structure. From a far distance, this is the complex. And when you take a cross section, as you can see, this is the hill on top, and then you start excavating and going down, going down. And the interesting thing, unlike the first example where I have shown you a deep excavation, there is nothing on the other side of the excavation. So the earth pressure completely pushes this block forward. And at locations where you have high-rise buildings, there is a very heavy weight, so that increases the frictional forces. But at some locations, you have only 3-4 story high structures. For example, this tower is on the background. So here in front, you have only these maybe 9-10 story high buildings and an enormous earth pressure acting from behind. So the lateral stability became a problem. And we went so far as to get rid of the water isolation barriers, because they were reducing the friction coefficient extremely. So we said you have to provide watertight foundation concrete in order not to use any geomembrane or similar barriers for water isolation. And we went even so far as to build a laboratory experiment where we determined experimentally what the friction coefficient between the fresh cast in concrete and the in situ soil was. Here you see a more detailed cross section. This is the hill. As you see here, right in front, there is almost no load, but there is an earth pressure. But all these slabs and vertical walls are interconnected, so they are, as a whole, are pushing this mass to the front. So the total elevation difference, I forgot to mention, was 60 meters from the top to the bottom. So you can imagine what the horizontal earth pressure is. Here, the code, as you can see, is 106, and at the bottom is about 46. So the elevation difference is approximately 60 meters. And as I said, there are different buildings. For example, here you have some towers, and here you have some deeper excavations for the service cores, etc. And the stresses are also extremely difficult that are transmitted by the buildings. For example, here you have only 20 kPa of vertical load, which is extremely low. This pink area has 100. Here you have 700. Here you have 100. Here you have 165. Here you have 300. Here you have 750, 500, 600. So there is no way you can analyze this using a two-dimensional finite element. So again, a three-dimensional finite element was needed. And as I said, if you conducted the analysis with a simple hand calculation, this mass was not remaining stable. So we also had to incorporate into this analysis the deeper excavations that were needed for the elevator pits. And at one location, we even needed a shear key to be added. And here you had the vertical elements of the structure of the foundation. So it was a quite complex analysis. And although the material, the foundation material, was a weathered rock, at the extreme heights of buildings, some of them even needed tile foundations. So besides surface foundations, some portions were also supported by deep foundations. So there's a mixed analysis here. So here you have some piles, here you have some shear keys, here many different elevations at different locations. For example, when you look to the settlements, they vary within this portion of the complex between 3 and 30 millimeter. So there is a tenfold difference. Horizontal displacements at the back are up to 8 millimeters, and at the front they remain 0. The horizontal earth pressures was one of the key questions that have been asked, and in the literature, when you look to a shear key, actually, you don't know what the pressure in front and on the back of the shear key is. Theoretically, in the front, you can expect a passive pressure, and on the back, an active pressure. But if you think that for the passive pressure to develop, unacceptable deformation is needed, we know that passive pressure is never reachable. So this analysis showed, for example, as the pressure on the back of the shear key was in the order of 150 kPa, on the front it was 350 kPa. So there is a threefold increase in the pressure. However, when you typically compare an active with a passive pressure, you have a tenfold increase in the pressure. So obviously, if you use this huge pressure in front, that would not be realistic. The axial forces on each and every pile were calculated. Bending moments and shear forces on piles have been calculated. So this brings us to the important subject of soil-structure interaction. Actually, also in the previous example, what we did was a soil-structure interaction analysis. But here in this case, the soil-structure interaction is much more pronounced. That was a project which was in Marmaris, a seashore hotel that was constructed with a very interesting idea. There was a rock plateau, and here was the sea. So what the architect has thought was, let me put the bedrooms of the hotel to the front, as you can see here, and put the restaurants and like other common areas of the hotel on the rock plateau. And obviously there was maybe a rock cliff here. So they put some backfill here and also tried to improve this with some piles, and they constructed the structure. But before even they were able to open the complex, extreme deformations started to occur. So they couldn't understand what the reason was. So again, we conducted a three-dimensional finite element analysis representing all different soil types and the foundation slabs of the upper foundation and of the lower level foundations and the rock strata here, and all the pile foundations underneath the common areas and under the hotel block. And we certainly observed that because of the fill in the bag, this portion was pushed to the outside, and this portion was being dragged to the inside. So the structural element were experiencing some stresses for which they were not designed for, and therefore were cracking. So the lesson learned from this project was, in contemporary geotechnical engineering, three-dimensional analysis, which analyzes both soil and structure, are becoming more and more necessary. So we couldn't have solved this problem by just analyzing the soil. We had to analyze in the same model also the structure. And that is probably where the engineering trends will go in the future. As you know, nowadays, the structural engineers do the structural design assuming there are springs under the building, and we geotechnical engineers design the foundations as if there is a load, an independent load acting on the soil. However, in some complex problems, these two must be combined, so there must be a common solution which both shows the stresses and deformations in the soil and the structure as well. Here is a metro bridge on Golden Horn. If you have been to Istanbul or have heard about the Golden Horn, it's a very nice and picturesque place. And this is the historical old town of Istanbul with the Süleymaniye Mosque in the distance. And this is a new metro bridge that needed to be constructed. And in order to provide a low profile, it had only two towers. And when you look to the geotechnical cross-section of Golden Horn, it is unique because unlike a river, in most big cities, there are rivers, but the depth of the river is limited maybe with 5-10 meters. But here, the depth of the Golden Horn is about 30 meters, and there is another 30 meter of extremely soft clay. Most of it is even not normally consolidated, but under-consolidated. So if you want to build even a pile foundation under these towers, the lateral stability becomes a critical issue. And it also dips from the shores, and at maximum, the bedrock has a depth of 76 meters from the water level. And the water level reaches at certain locations even up to 38 meters, for example, at this location here. So the problem is, as I said, the lateral stability, and you have to consider Istanbul is an earthquake-prone zone, so these piles have to also resist in earthquake. So the pile construction in such deep waters is either uses driven piles, but if you produce a driven pile, it comes to the bedrock and maybe can penetrate the bedrock for 1 meter or so at max. But for lateral stability of a 76 meter high pile, this is certainly not sufficient. So, and to construct a board pile in the open sea is not very often done. It's a very challenging operation. So what was found was that first 200 2,500 millimeter, that means 2.5 meter diameter piles were installed into the soft soil. So this is like a driven pile. And they are being driven with the help of hammers, as you can see. And then a grab is lowered into this and excavates the soft soil that accumulates, that remains in the driven pile, opening the, and then a rock boring cutter is lowered, and from inside of the driven pile, it bores the rock with the help of a rock bit and discharges the rock material to the outside. And of course, the reinforcement cage is also huge. And the lesson learned from this project was, for a proper geotechnical design, the engineer should be aware of all available technologies. Sometimes a certain installation can only be possible if the appropriate equipment is available, because we may design theoretically, but if there is no equipment which is capable of applying this design, then this is not worth anything. So the duty of a geotechnical engineer, not only for pile foundations, for any installation, he should be aware of modern technology available. Another interesting case is the Balaban landslide. This is a town area close on the shore of the Marmara Sea, and here you see an area which is not populated. You see a dense population of houses and buildings all around, but this area had been left empty. It is a formation which we call on top Bakırköy Formation, which is a limestone, and then it has a clay, sand, and clay layers underneath. So basically, these are soil, and this is a rock. On this area, which was left empty, in the recent time, they allowed buildings to be constructed. And for example, this is already a collapsed building. And these buildings started tilting because there was a huge landslide. You can see the tension forces, the road folded, the pedestrian walk. So huge landslide. And we did a very extensive investigation using a lot of extensometers that go as deep as 100 meters. And here you see on the top the limestone layer in these cross sections. And for example, this is the layer below the limestone layer. And as you see here, they are discontinuous, or this layer of gravel continues here, continues here, continues here. So we were able to determine all these landslides that had occurred in the past. And because of some unknown reason, these landslides were reactivated. And the depth of the... So we, of course, had also geologists on our team, and they produced this model, which they call a paleo landslide, which means it's a historical landslide. And that's why actually experienced engineers had left this area by itself. But later on, because it has a beautiful view on the seashore, people wanted to construct here, and they reactivated this historical landslide. And it was such a problematic case because the depth of the sliding was about 90 meters deep. So the mass that was sliding into the sea was huge. It was not stoppable. And because it was also below the groundwater table and below the sea level, actually, you couldn't take a drainage measure either. So eventually we had to evacuate the whole area. And it was a kind of a human tragedy, actually. So the lesson learned, understanding the geology is of crucial importance to geotechnical design. Hence, it is not enough to determine the geotechnical parameters for design alone. We need to understand the formation and history of the site in order to avoid problems. Another interesting project and interesting solution I want to share with you is a highway project. This is an interesting project because there was an existing road connecting two cities along this route, and then a dam had been constructed, and the water in the dam reservoir flooded these areas. So this shore, and an intermediate island remained in between along this route. So the Highway Authority of Turkey decided to build two short bridges. And the peculiar thing was the boundary between different sections of the Highway Authority was passing right through here. So this bridge has been constructed before the water was accumulated, but this section of the Highway Authority delayed the construction of its bridge, and as soon as the dam was constructed, siltation started to fill the reservoir, and that is, of course, another major problem in Turkey in dams, the siltation. So when you look to the geological cross-section, you see the gravel and the bedrock, and you also see that the bedrock is not very uniform actually. But what is above here is the brand new sediments that have been brought and settled here in the reservoir of extremely soft silts and clays. So as you may recall, this resembles a little bit like the Golden Horn crossing. But of course, the Golden Horn crossing was a major metro project for Istanbul. So they were able to bring extremely expensive equipment and through international waters into Istanbul, of course. And this is a small town in Anatolia, so you cannot bring this extremely expensive and sophisticated equipment to the site. And if you install a pile, again, you have a very soft clay and a bedrock at the base, and the depth here is about 16 to 18 meters. And because water will be filled, you have another 20 meters up to the bridge deck. So you have a 40-meter high bridge pier, of which only 20 meters is embedded in an extremely soft clay. And they couldn't build an embankment either because this soft clay, and the problem was that they couldn't construct this portion of the road. So to solve this problem, we suggested to use geosthetic encased columns, or the so-called GECs. GECs are very interesting solutions. They are basically stone columns, but if you have an extremely soft clay, also the stone column cannot keep its stability, so they will fail in bulging when you apply a vertical load and there is not enough confinement in the soil. So here the confinement is provided by a geostatic product. So when the vertical load is applied and the stone column wants to spread laterally, it basically creates a tensile force in the encasement and thereby prevent this lateral spreading. And with this, it creates a column of a quite high elastic modulus. So therefore, the uniform load of the embankment is distributed unevenly on the soil and on the column. And here you see, because above the column, the vertical load is high, and in the surrounding the soil, the vertical pressure is low. Also, the lateral pressures outside are different than from the inside. And actually, this difference is the reason why a tensile force is developed in this encasement. And when you have several columns, the load is distributed actually to these columns from the overall embankment by the help of arching. Here we see the typical cross-section suggested. Here you see the soft sediment. Here you see the current water level. And here you see the project elevation of the road. So quite a number of geosonic encased columns have been placed underneath the embankment, and a reinforcement at the base prevents differential settlement between soft soil and stone column. The construction was also done in a simple way because, as I mentioned before, no big barges, etc., could be brought to the site. So basically what the technique used was a pipe was being lowered from the edge of the fill, and it was filled with the encasement and then the stone column, and then new material was dumped, and the progress advanced in this fashion. Here you see a photograph, the crane standing on the existing fill, driving the pipe, and on a very small barge there is a small excavator. Here you see the lowering of the geosonic encasement and then filling of the inside of this encasement. So as you see, this embankment is in progress. This project has been completed and successfully served. A metro tunnel passing underneath a river with a diameter of 11 meters. Here, for water isolation, a GCL was used. Initial installations worked successfully. The total GCL installation for the current projects will reach 1 million square meters. And traditionally, as you know, PVC liners are used in tunnel liners, but they are very vulnerable because they are very thin. So if there is a fault, there is a hole, water will leak through. But I'm not sure whether you are familiar with the GCL. It stands for geosynthetic clay liner. It's basically a bentonite clay in between two geotextiles. So the impermeability is provided actually by this bentonite. And therefore, even if there is a rupture or puncture, etc., the bentonite swells and seals. So it's almost a self-rehabilitating barrier against water. Another geosynthetic application that I would like to mention brings favorable solutions are the geosynthetic reinforced retaining walls and slopes. This is the Bosphorus. This is the second Bosphorus bridge. the municipality wanted to construct a shortcut from the shore, coming up the hills and joining the highway that crosses from Europe, going all the way to East Anatolia and even to Iraq and Iran, etc. So part of the retaining walls were constructed with the reinforced wall technique. Here you see a segmental wall which has been constructed to build the wall. This technique allows the fill to be constructed as the facing is made of concrete blocks and there are geostenic reinforcements. But at this location, there was a major problem because the foundation soil was quite weak and they couldn't excavate the foundation soil further because it was at the edge of the highway embankment, and this was a soft soil, soft layer. So actually you either had to remove this, but this would harm the stability of this highway slope. So instead of a wall, we decided to build a geostenic reinforced slope. And the total height of the slope is 40 meters. And here is a cross section. There was a very limited excavation on the embankment of the highway. Here is the highway embankment at this level. And these are all reinforcements, and the facing is also constituted with the reinforcement. Here is a completed picture, and as you can see, the height comes from a minimum value, increases significantly at this location where there is a weakness of foundation soil, and actually transmits or transfers to the section where you had a concrete block facing segmental wall. And this wall also is inclined to align with the reinforced slope, but then gradually its slope increases and turns into a wall. And here is the slope from a distance, and back here is the highway. Here is another reinforced soil structure example. This is again a dam reservoir, and road must be elevated so that when the reservoir fills this area, the road can be continued. And these culverts are constructed so the water on both sides of the embankment can flow easily from one side to the other. Here is another view of the same. Here is a green Terra mesh application for a highway in Istanbul. And here is a bridge abutment constructed with the reinforced soil technique. Again, some wraparound MSE type of walls in this picture. One recent project is the Northern Marmara Highway, which tries to reduce the traffic passing through downtown Istanbul. And at this location, in the plan, you see that's a road, and you have they are crossing some valleys, so there are extremely high embankments. And from the side view again, you see how high these fills slopes are at one location, the height of the reinforced soil slope reaches 43 meters. This is during the construction. The lessons learned from these last examples are is that using geosynthetics can solve some of our geotechnical problems in an efficient way. Using geosynthetics makes sometimes otherwise almost impossible solutions constructible. They definitely reduce the cost, they often shorten the construction time, and geosynthetics provide sustainable solutions. This means lower carbon dioxide emissions and obviously uh, good for the contractor and civil engineering community, costs less because carbon dioxide emission doesn't happen free of cost. When you produce carbon dioxide, that means you are burning fuel, which means you are burning your money actually. With this, I thank you for your patience, and if you have any questions, I will be happy to answer them.